A block with mass m is being pulled by a constant force F and is accelerating on a horizontal surface. The force F makes an angle theta with the horizontal. The kinetic friction coefficient between the surface and the block is mu k, the coefficient of kinetic friction. Find an angle theta that gives the maximum acceleration. So let's start by drawing a free body diagram for this block. So let's say that this point is the block. Then you will have a force F pulling at an angle. Of course, you have the normal force and the force of gravity. And pulling to the left, lines aren't straight today, but pulling to the left, you have the force of kinetic friction. Since it's accelerating on a horizontal surface, so it's moving, so the friction is kinetic friction. And in our reference system, upwards is the positive y direction, and the direction to the right is the positive x direction. So from here, we can use Newton's second law to write a few equations. So we can decompose this force vector into its individual components. And this is the angle theta shown in this diagram. So this becomes F sine theta, and this component becomes F times the cosine of theta. So you can start, let's write it first and use Newton's second law for in the x direction. So in the x direction, you have the force times the cosine of theta pointing to the right, to the positive x direction, as well as the force of kinetic friction pointing to the left, or in the negative x direction. And that is equal to the mass m times its acceleration. I'm going to call it ax for clarification, because this is the acceleration in the x direction. And we can also do this for the y direction. We have the normal force plus F sine theta, which is also helping pull the block up, and minus the object's weight, or mg, which is acting in the negative y direction. That is equal to mass times the acceleration in the y direction, which is 0 since the block is not shooting off into the sky or falling through the floor. So we can say that the normal force plus F sine theta is equal to the force of gravity, mg. So we need to figure out what this force of friction is. So we know that the force of friction, or force of kinetic friction, is given by the coefficient of kinetic friction times the normal force. And we can solve for the normal force from this equation, where the normal force is equal to mg minus F sine theta. So then the friction force, the force of kinetic friction, becomes mu k, the coefficient of kinetic friction, times mg, the weight, minus F sine theta. And now we can plug this back into our first equation here. So our first equation becomes the force times the cosine of theta minus mu k mg. And remember, there's a negative sign here, so these two will cancel out. So when you distribute it, the negative sign here and this negative sign cancel out, and you'll get a positive. So plus F sine theta, and that is equal to the mass times the acceleration. Also, I dropped the subscript since there is no acceleration in the y direction, and the only acceleration is in the x direction, so I don't need any subscript. And from here, we can factor out the force. Oh yeah, don't forget about this coefficient of kinetic friction. So you get the force times the cosine of theta minus the coefficient of kinetic friction times sine theta minus the coefficient of kinetic friction times mg is equal to the mass times the acceleration of this block here. So I'm going to erase some of this to make more room. There we go. And now we can solve for the acceleration. So dividing both sides by m, we get that the acceleration is equal to the force divided by the mass times the cosine of theta minus mu k sine theta minus mu k mg. And that is an expression for the acceleration that we have solved for. And it's sort of in terms of this force and the angle. It's in terms of the angle theta. So we need to figure out the angle theta that gives the maximum acceleration. So the maximum acceleration is when the rate of change of acceleration with respect to this angle theta is equal to 0. And this is when the acceleration is at its maximum. And this is because if I try to draw something like this, where you have an axis representing the value of theta and the acceleration, it might look something like this, where the rate, if you look, this might be a graph of how the acceleration changes as you change the angle theta. And you'll notice this peak is going to be the maximum acceleration. This is the angle theta that gives the maximum acceleration. And the slope of this, or rather the rate of change of the acceleration with respect to the angle theta, is going to be at its minimum. Whereas if you take the slope at like some other angle, the rate of acceleration change is going to be a lot larger than the rate of acceleration change at the maximum acceleration. So that is why we can use this derivative here. So this equation needs to satisfy this derivative expression for it to be true. So we can take the derivative of both sides of this equation with respect to theta. So dA over d theta, that's the maximum acceleration. Actually, I can save some space if I just write it over here. The rate of change of acceleration with respect to theta is equal to the derivative with respect to theta of this whole expression here. And I am actually kind of running out of space, but just know that I'm just writing this whole expression down here again. So this expression is what we have down here. And this whole thing must be equal to 0, since we have established that the maximum acceleration is when the rate of acceleration change with respect to the angle theta is 0. So now we just need to differentiate this equation. So we get that f over m times the derivative with respect to theta of the cosine of theta plus the derivative with respect to theta of mu k sine theta must be equal to 0. And if you remember this term, we can actually remove it, because the derivative of this with respect to theta minus mu k mg with respect to theta is simply equal to 0, because there is no theta term, and this whole thing is all of the values in here are constant, and the derivative of any constant is going to be 0. And we can also move the force divided by mass out, because it's also a constant. So this will give you, differentiating both of these with respect to theta, you get that the force divided by the mass times minus sine theta, that's the derivative of cosine theta with respect to theta, plus mu k cosine theta, and that is going to be equal to 0. So now if we multiply both sides by m over f, this is so that we can cancel out this value here. This is still going to be 0, so this can get rid of that, and these two values will cancel out too. So we get that minus sine theta plus the coefficient of kinetic friction mu k cosine theta is equal to 0. Can move sine theta over to the other side, that's equal to sine theta. And this, I can actually say that it's theta max, since this is going to be the angle that gives the maximum acceleration. But I don't really want to use the subscript, so just know that this angle is the angle of maximum acceleration. And if you divide sine theta by cosine theta, you get tan theta, the tangent of theta. It's a trig identity, and that's going to be equal to the coefficient of kinetic friction. So we just have one more step, and we can solve for theta. So the theta, and this is the maximum, the angle for maximum acceleration, is going to be given by the inverse tangent of the coefficient of kinetic friction, or mu k. And this is the expression that gives you the angle theta that gives the maximum acceleration. And of course you can go further and solve for the maximum acceleration with this angle theta, but the question here only asks for the angle theta that gives the maximum acceleration. So this is how you would solve this problem here.